We've got Dan Friedman coming up next from NREL, National Renewable Energy Laboratory. Let me get his little introduction up quickly, or maybe actually, why don't you go ahead and introduce yourself, and you can go ahead and start your presentation.
All right, thanks, Weston. Can you just give me a time check how many minutes this should be?
Sure. Let's do about 10 minutes, if that's all right.
Great. Yeah, so thanks, everybody. Yeah, I'm Dan Friedman from NREL, where we do a lot of PV and are getting more into specifically laser power PV. So this talk is intended to be kind of a primer on kind of use considerations. And the talks we've seen earlier today and yesterday, I think really kind of set the stage for it and gave a lot of great kind of general overview. So it's really thanks to that. Next slide, please. So these, as you kind of heard previously, the highest performing devices, which you're going to make these laser power converters, are so-called 3-5 materials because they're based on COM3 and COM5 periodic table. So you heard previously about InGas as one example, or gallium arsenide. These materials are give you devices that are of the highest efficiency. They're very well proven, and for laser PV especially, they can be kind of designed and fine-tuned to almost any wavelength that you might be interested in, ranging from 600 to 2500 nanometers. Realistically, you're probably not going to be interested in such a wide range, but if you were, you could be. One thing that should be noted is that these the one downside of the 3-5s is they're relatively costly, something like on the order of magnitude of $1 per square centimeter. Now, if you're producing in these applications, kind of to convert that into dollars per watt, if you're producing a watt per square centimeter, so that's $1 a watt, that might or might not, you might or might not care about that level of cost. What's important for me to communicate is that there are significant cost reduction kind of projects underway. There's certainly a big one at NREL, and there are efforts going on kind of throughout the 3-5 community I could talk more about if people are interested in, that are aiming to bring those costs down by, at least an order of magnitude. So next slide, please. So one of the big advantages, but also challenges for using and designing these devices for laser receipt of laser light is that you can accept very high input power densities, which enables you to transfer more power. That's obviously desirable, but it's also a challenge because the more power you're converting from a laser, the higher the currents that the device is producing. And for example, I give an example here. If you're talking about a 10 watts per square centimeter of kind of light at a typical laser wavelength, that's literally amps per square centimeter that your device is putting out at 1 volt. That's an incredibly high current, low voltage device, which is not what you want for mitigating series resistance. You really want to bring those currents down so you don't lose excessive power to good old, I²R losses. And there are various strategies for that, but probably maybe the most important one to talk about is to split up to divide that light into multiple individual little mini solar cells or junctions. You can do that. I illustrate in the bottom half of this slide 2 ways to do that. One is you could have a lot of little individual solar cells kind of laterally and interconnect them in series. The other shown below is that you could stack those individual solar cells one above the other, and that essentially, assuming you design it right, that essentially has the same effect, where some of the light is absorbed in the top junction and some in the second junction and so forth. And it has the same effect of reducing the current and increasing the voltage. And this is a very, very effective way of doing things. When if you were to kind of look at a spec sheet for one of the manufacturers, you'd see that probably most or all of them actually do this, and they can use, sometimes they use both of these strategies, and that's why. Next slide, please. So let me talk about the state of the art. This is not trying to be comprehensive, but just picking out prominent examples from both the laboratory and commercial products. So in the laboratory, the group at Fraunhofer Institute for Solar Energy recently demonstrated a PV receiver efficiency near 70%, absolutely amazing. And that certainly, they're getting close to efficiency limits. Then on the commercial end of things, we've heard a lot about the great results from Spectra Labs. So they're one of the, there are probably multiple commercially available, commercial vendors of these very specialized devices. I'm aware of kind of Broadcom, Spectra Lab, and Azure Space being especially prominent. They're all, they're not quite at the kind of that near 70% level, but they're all very, very good. Typically above, 50% PV receiver efficiency. They're packaged. You can get them packaged, as shown here, for very kind of robust for just plug and play into your application, and various configurations are available. One thing I would say about everything that's shown on this page is these devices are all, the collection areas are all small, and potentially, you might want something larger. So that's something to be considered. Next slide, please. So this was touched on earlier, but it's kind of interesting. So I thought, and good to, it's one of these things that, if you encountered it by accident, you would be unhappy. So I thought I'd mention it, which is the temperature dependence of these PV devices, these laser PV devices. In solar cells, we're used to a pretty simple situation where when the temperature goes up, or the performance, or let's put it this way, when the temperature goes down, the PV efficiency slowly goes up. And that's it, nothing dramatic generally ever happens with that. That just keeps happening. You lower the temperature more, the efficiency goes up more. With the laser situation, it's similar until it becomes very different. And that's because, and again, this was discussed earlier this morning to some extent, but that's because you're only converting one laser wavelength, and solar semiconductor band gaps generally increase with decreasing temperature. So there is the potential, if you had your laser wavelength very close, just barely, your laser energy just barely above the PV cell band gap energy, and you started cooling the PV cell, there comes a point where relatively suddenly the PV cell would no longer be collecting the light at all. And so you would get a situation like shown in the red curve here, where you start out, you're thinking, you designed your cell, or you chose it to operate at 50 C with a given laser wavelength, and that was great. But then you actually, it turns out that you actually need the cell to operate at 20 C as well. And in that case, it turns out that you probably didn't design the cell quite right. So by giving up a little bit at the higher temperatures, you can just kind of get rid of this problem at the lower temperatures as shown in the blue. So consider the entire range. This is not a problem at all. It's just something to be aware of. You consider the entire operating range of temperatures when you choose your cell. That's all. Next slide, please. So just about done. I'd say future developments will, I think, continue to say even further increases in performance, and especially for materials, for band gaps, wavelengths, other than kind of the standard gallium arsenide at 1.42 eV. So if there were an interest in lasers at significantly different wavelengths, I think we'll see continued improvements there. Also, cost reduction. Didn't talk much about that, but that's going to happen. That is happening. And finally, I would say, we mostly what we have is relatively small area cells, so there'd probably be more emphasis on larger area applications. And with the next slide, I'll just stop there. Thank you.
Great, thank you very much. And there'll be an opportunity to discuss some more advanced PV receiver materials in the breakout. That's one of the ones that's specified for that time.